Okay, so here we're going to take a look at, we're going to jump into the natural exponential. So we did a lot of work kind of defining the natural logarithm and some of its properties. And now we're going to kind of work off of that, right? We set a lot of the foundation to kind of now take a look at the natural exponential function, right? Which for now, we're going to define this number e. Right, you're all familiar with one of the most famous mathematical constants, right? The natural number e. So this is how we define it in math, right? In terms of here, what it represents. The natural number e is the number that gives you a unit area or an area of 1 under the curve 1 over t, right? So that is it, right? That is how we define it. All right, now I'm going to come back to that in a second here. But we want to build off of what we have so far, right? Now, so far we have the natural log. Actually, let's... All right, so we have y equals to the natural log of x, right? Where domain is from 0 to infinity. And then the range is negative infinity to infinity. Now, this is a one-to-one function, right? It's always increasing. That's what the derivative tells me. Okay? All right, so it's always increasing, right? Not at an incredibly high rate, but it is always increasing. Now, if it's one-to-one along its domain, that means that it must have an inverse. Right, and inverse that graphically looks like this, right? If this is kind of reflected across this line, then it crosses this point here. And it has this, right? So this will be the inverse of the natural log. For now, I'll just call this exp of x. Now, what I know about this exponential, this exp function, which you'll guess that we're going to come to the conclusion that it is the natural number e, right, is that the domain here is going to be from negative infinity to positive infinity. And our range is going to be from 0 to infinity, right? Again, properties of inverses. This is what inverses tell us. All right, so now we're after to determine, well, what is this exp of x function? All right, and we could see, again, we'll derive it, right, using what we know so far about our exponential and about our inverse functions. The exp of x is equal to y if and only if, right, the natural log of y is equal to x, right? Again, that's just the definition of inverse functions, right? And also that the exponential exp of ln of x is equal to x. And again, these are for values of x bigger than 0. All right, and then the natural log of exp of x is equal to x, and this is for all real numbers. Right, since this exp function has a domain of all reals, which we see here, right? And notice that it can be any real number as the input because the output is always positive, so we can always take the natural logarithm of it. So this still holds for any real numbers, whether those numbers x are positive or negative. The resulting operation of exp is a positive value because that's the range of the exponential. All right, and then other special points here, the natural log of 1 is equal to 0. And that also means that because of this exponential or this inverse relationship, the exp of 0 must equal to 1, which we see from the graph as well. Okay? All right, and then let's see. And also, inverses tell me if I take the exponential of the natural log, hold on here, oh, excuse me. here. If I take the natural log of e, by definition, we said that was 1. Well, that means that the exp of 1 has to be e. Okay, so now that leads us to, well, what must be the base here of this exponential, right? Well, almost there, right? Here we have, if we recall here, a property from the natural logarithms is we have this is equal to r ln of e, but we already defined that the ln of e is 1, so this result is r. Okay, so what that means is, again, through properties of inverses, the natural log of this exp to the of e to the r is equal to r. Right, that means that this is true if we think of inverses, that expr must equal to e to the r. So now in general, right, all this means is that this inverse function exp is in fact the exponential of base natural number e. So e to the x is our exp function x. All right, so now we can rewrite all of those properties, but instead of this and a mysterious exp inverse function, we know it's the exponential with base e, the natural number e. Okay, so that means that if I have e to the x is equal to y, this is true if and only if the natural log of y is equal to x. And e raised to the ln of x is equal to x for x bigger than 0, or the natural log of e to the x is equal to x, and this is true for all x. All right, now some also properties that we can gain from the graph here is that the limit as x goes to negative infinity of my e to the x is 0. Now it never actually becomes 0, it just approaches 0. The limit as x goes to infinity is e to the x. Okay. All right. And now that with these kind of limits, these infinite limits in hand, we can expand the type of limits that we can evaluate. So we could say, all right, what is the limit as x goes to infinity of e to the 2x over e to the 2x plus 1. All right. So we can start by doing something like this. We can multiply by 1, right? Mathematicians' favorite trick, multiplication by 1. In this case, 1 comes in the form 1 over e to the 2x times 1 over e to the 2x. And the resulting limit is 1 plus 1 over e to the 2x. All right, and then limit laws allow me to simply rewrite it like this. And I know that the exponential is going to infinity, so 1 over, or a large number, 1 over a very large number is 0. So we get 1 over 1 plus 0, which is simply just 1. Okay. All right, so now we can now do limits like this, right? Because of our knowledge of the exponential. All right. Now some other properties here, or laws of exponents that, again, we've seen before, right? E to the x plus y equals to e to the x, e to the y. And then e to the x minus y equals to e to the x over e to the y. And then also e to the x raised to the r is equal to e to the rx. Okay. All right. And then from here, so we could see, all right, so knowing those, let's prove one of them. Let's prove this first one here, right? And again, right, our proofs here have all been calculus-based, right? We've done this in algebra where we just kind of had these limit laws that we kind of had some, if you were shown a derivation, some form of algebraic derivation. But here we're strictly going to look at calculus and essentially based on what we've already discovered about the natural logarithm. So I'll start with this one, e to the x plus y. Oops, excuse me, let's start it like this. E to the x, e to the y. All right. Now, previous property that I've proven about the natural logarithm is that I could split this up in addition. All right, and then another property told me I could bring this out in front, but the natural log of e is just 1. Same thing here. Y becomes a coefficient, but the natural log of e is also just 1. So we're left with x plus y. All right. And here, so we have the natural log of e to the x, e to the y is equal to x plus y, but properties, ln is a one-to-one function, and I know whose inverse is the exponential. So by the properties of inverses, e to the xy must equal to e to the x, e to the x times e to the y must equal to e to the x plus y, right? Again, these are just properties of the inverses and how the inverse of the natural log, how the natural log and the exponential are related. Okay, so that proves a property. Now let's go to, well, what is the derivative of this exponential, the natural exponential? Okay, so here I want to prove that the derivative with respect to x of e to the x is actually the function just e to the x. Okay, really straightforward, right? So here, how are we going to show this? So let's start off again with our function y equals e to the x. Okay, and I'll start by taking the logarithmic differentiation approach that we covered previously. So that means that the natural log of y is equal to the natural log of e to the x. All right, but x comes as the coefficient, and the natural log of e is just 1, so we're left with x equals the natural log of y. All right, and now I'll take the derivative of both sides here, right? So we'll take here the derivative dx with respect to x. Again, implicit differentiation here. Right, so this becomes here 1 over y. Again, y is a function of x, so y prime. And the derivative of x is just 1. So we get y prime equals to y. Right? Really our first kind of differential equation, right? If you think of in differential equations, you'll get into, this is the most basic differential equation where we have an equation involving the function itself and its derivatives. And for this one, we see our solution is up here. Right? So we have y prime equals to e to the x. In other words, we've proven our desired result, right? The derivative of e to the x right, with respect to x is just e to the x. Now, if that exponent is some function of x, so dx e u, right, some function of x, then we'll have the chain rule, right? We'll get e to the u, and then derivative du dx. All right, and an example of that, so let's work through an example of what that would look like. Is here, let's say we had, all right, let y equal to e to the negative 4x sine of 5x. Oops. And I want to find y prime here. Okay, so y prime here. Now be careful here, right? Because we have several things going on here, right? We have a product, and we also have a chain rule as well. So when I find the derivative, I'll start with this function, right? Again, chain rule says just take the derivative of the outer function, which is just the exponential. So it's just e to the negative 4x, and then take the derivative of this inner function, which is negative 4x. Derivative of that is negative 4. And leave the other function alone, sine of 5x. And we're going to add to that. Now leave the exponential function alone. And take the derivative of sine 5x. The way I do that is, again, a chain rule. But here, outer function, cosine, leave the inner function alone. So 5x, and then derivative of the inner function, which is going to be 5. And there we go. We found the derivative. Okay, and now the integration is pretty straightforward as well. Okay. Okay, hold on a second. All right. Okay, where was I here? Okay, let's just keep going here. Okay, the integration portion of this. So if you want to integrate, all right, since we know that the derivative sorry, having some technical difficulties here. All right, let's see here. This thing gets it together here. So if we're going to be dealing with integration, all right, so here, this is going to come from so if we know that the derivative of the exponential is the exponential itself, well, that means that the integral, the antiderivative, of e to the x is just e to the x plus c. So now we have another formula integration. All right, so now we can use that along with other techniques that we use, mainly the substitution, to do something like this. Okay. All right. So for our example here, we'll have the integral of 6x to the 3x squared dx. Okay, so using a u substitution here, we'll let u equal to 3x squared. And then du is equal to 6x dx. All right, which we see out here, right? So doing our substitution, we get the integral of e to the u du. And that is the most basic one, so it's just e to the u plus c. All right. And that equals to substituting e to the 3x squared plus c. Okay.